In this video, we're going to find the Laplace transform of a number of piecewise functions using the definition. So a quick reminder of the Laplace transform. This function is going to take in functions of t and spit out functions of some new variable s. And the way we're going to do this is by using an improper integral. So for all s where the improper integral converges, the Laplace transform of the function f of t is going to be the improper integral from 0 to infinity of e to the negative st times this function f of t dt. So as long as this improper integral converges, our Laplace transform f of s is defined. Notice that we're integrating with respect to t, and we have these two variables s and t appearing in the improper integral. So since we integrate with respect to t, this produces a function that is strictly in terms of s. So this is the definition that we're going to be using today. So we want to use the definition to show that the Laplace transform of this Heaviside function is given by e to the negative as over s, where this a tells us when the Heaviside function turns on. Okay, so let me remind you, this function is off when t is less than a, and then when we arrive at time a, our function turns on. So using our definition, the Laplace transform of this function is going to be this improper integral from 0 to infinity of this Heaviside function times e to the negative st dt. And remember, this function is 0 if t is less than a, and it's 1 when t is greater than a. If it's equal to 0, then this integral is going to be 0. So rather than integrating from 0 to infinity, we can integrate just from a to infinity. When it's on, it's just equal to 1. So this is the integral from a to infinity of e to the negative st dt. And we can write this as the limit as t goes to infinity of our antiderivative here is negative e to the negative st over s. Oops, maybe I'll put that negative down with the s. So we just do a little u substitution here. And we're evaluating between a and t. And to help us see what this looks like, I'm going to put this negative exponential in the denominator for the first term. We see we're taking the limit as t goes to infinity of 1 over s times e to the st. As long as s is greater than 0, this limit is going to 0. As t gets bigger and bigger, we've got this exponential growing in the denominator. And so this is going to be equal to e to the negative sa over s. As we've got two negative signs that cancel out to be positive. Remember, we needed s greater than 0 so that first we're not dividing by 0, and also so that this exponential is going to go to 0. In this next theorem, we're going to compare the Laplace transform of a function f of t with a shifted version of f. So let's start by looking at the Laplace transform of f of t. So Using our definition, we know that this is going to be the integral from 0 to infinity of f of t times e to the negative st dt. And if we imagine having a graph of f, what we're going to do is we start integrating at 0, multiplying by this function e to the negative st. We're going to be comparing this with the Laplace transform of this shifted version. Okay, and if we look at these two pieces, f of t minus c, this is going to be shifted to the right by c. And this Heaviside function means that our that we're going to be equal to 0 until we get to c, when we turn on this function f of t minus c. So in the second example, we're going to be looking at the shifted version of f. So we shift our function to the right by c, and we don't turn our function on, it's equal to 0 until c. So we take the same picture of f of t, and we basically say we're not going to start the function until c. Okay. So we can write down the definition using the integral. We want to interpret this piecewise function uc of t. This is going to be equal to 0 until c, and then it'll be equal to 1. So we know that integrating 0 is not very interesting. So we can write this as the integral from c to infinity of 1 times f of t minus c e to the negative st dt. And now this looks quite a lot like our original integral. All we're going to do is a little u substitution, a little substitution of variables. We're going to replace t minus c with, let's call it tau. Okay. This gives us the same, we don't need to change our variable of integration. And our lower bound is going to be c minus c, or 0. And our upper bound will stay at infinity. Okay, and so this changes to be the expression, the integral from 0 to infinity, f of tau e to the negative s, and here we could solve for t in terms of tau. T is equal to tau plus c. So we can replace this power with tau plus c, d tau. Okay, we're almost done. This looks so much like our Laplace transform of just f. We can distribute this sum, and it gives us the integral from 0 to infinity f of tau e to the negative s tau times e to the negative cs d tau. And because this term e to the negative cs has no taus in it, we can pull it out front, outside of the integral. So we end up with e to the negative cs times our Laplace transform of f of t. I know we've got a new name here. We called it tau, but it's just a dummy variable, so it doesn't matter what we called it. We could change this to t or z or anything. But all in all, this is e to the negative cs times the Laplace transform of our function f. And so we arrive at our